Before we start talking about Thevenin's theorem, Thevenin's theorem, I wanted to take some time to explain what is Thevenin, what does Thevenin mean. It's actually named after a person. So let's get into Thevenin's theorem. Thevenin's theorem, what it does is it takes a complex circuit. So if we have something very complex with a bunch of resistors, and we have terminals A and B, and let's say we put something into A and B, we plug something in. So it could be like a cell phone, it could be a variable resistor or a computer. We put something between A and B. What we can do with linear circuits is then transform this entire circuit to a very simple circuit, which is just one voltage source and A and B. So these are equal to each other. So we can take a very difficult, very complex circuit and transform it into a very simple and very easy circuit. So we go from this complex circuit to this easy, simple circuit, So I will show you how to do this process. We now must look at independent and dependent. Do you remember the difference between independent and dependent? So we have one person, and this is independent. Independent, meaning alone. Alone. And if we talk about this would be dependent. Dependent. So independent, dependent. So this voltage source is independent. Dependent. Because it depends on Vx. What is Vx? So it is a dependent voltage source. And we must know the difference between these two to do Thevenin's theorem. So Thevenin's theorem. So to do Thevenin's theorem, we need to consider if no dependent sources. So if no dependent sources, step one, we turn off independent sources. That means voltage sources become short circuit. Current sources become open circuit. After we turn off independent sources, we find the equivalent resistance of the circuit. We find Req. So that's step 2. And then step 3, well, Req is then equal to R Thevenin. And then step 3, we turn on sources. So we turn the sources back on. And then we lastly find the voltage between the terminals. We find that open circuit voltage between the two terminals, and that is equal to the voltage Thevenin, the Thevenin voltage. So we take a complex circuit and then we transform it into a simple circuit that has voltage and then the resistance and two terminals. We have, this is our voltage here, our voltage. So that is 4 steps, and that is how we will do the process. We will now do an example here of a Thevenin equivalent. So I'm going to draw a circuit. So we have a voltage source, and that is connected to a resistor, which is connected to another resistor. And then in parallel, we have a current source there. And then that is connected to a resistor. And we can label this is 32 volts, 4 ohms. This one is 12 ohms. This one is 2 amps, and this one is 1 ohm. And in these occasions, what we usually do is put some sort of load here. So this can be anything. This is you can think of this as a load, just something that we put into that. Now we want to simplify all of this. We want to simplify all of this. So let's delete some of this stuff here. So we want to find the resistance between here and here. Whoops. Okay. So step one is to turn off all of the independent sources. So turn them off. So we need to turn off this 32 volts and turn off the 2 amps. So if we turn off 32 volts, that becomes a short circuit, and turning off this 2 amps then becomes an open circuit. So an open circuit there. So now we're looking for the equivalent resistance. The equivalent resistance, and that is equal to the Thevenin resistance, TH, the Thevenin resistance. So we have 4 and 12 here. Those are in parallel. 4 and 12 are in parallel. So we have 4 times 12 divided by 4 plus 12, and that is 48 divided by 16. And 48 divided by 16 is 3 ohms. So that's these two combined together. So we have this situation here. So we have 3, and then we have 1 ohm. And we can add those two together. These are in series. Those are in series. And we come out with the equivalent resistance, which is equal to the Thevenin resistance, which is 4 ohms. Okay. So that is the first part of this, but there is more. We need to do more here. We have the resistance. So what we do next is turn back on the voltage source, or the sources, the independent sources. We want to turn those back on. So we have 32 volts, and let's draw the circuit again. And let's label these. So we have 12 ohms, we have 4 ohms, and we have 1 ohm. And what we are looking for now is the voltage, the open voltage between A and B. And that is equal to the Thevenin voltage. So we're looking for the voltage here. So how do we solve this? KVL, KCL. For example, if we take the current flowing this way, what is the current flowing that direction? The current. Well, since this is open, this current must be 0. So this must be equal to 0 because it can't flow this direction. Okay? So how do we do this? Well, let's look at KCL here at this node here. KCL at the node there. So what we have is the voltage is our Thevenin voltage here, if we say that this is ground, right? These are equal because there's no current flowing this way. So that is our Thevenin voltage here. And so what we have is we can do KCL, and this is 32 volts here, right? 32 volts. And this is all our Thevenin voltage. This is all here. So doing KCL at this point here. So let's say this is I0 and this is I1. So KCL, let me grab a different color. KCL. Ugh. KCL at this point. So we have coming in is I naught and plus 2. The 2 is going in. And going out, we have I1. And we already said that this voltage, if we want to call this I2, is 0. Okay? And that is equal to 0. So I naught here is equal to 32 volts here minus V Thevenin, this voltage here, divided by the resistance, which is 4, plus 2 minus V Thevenin divided by 12 equals 0. Okay, so we can solve this equation. And how do we do that? If we multiply this by 12, we get 3 times 32 minus V Thevenin plus 24 minus V Thevenin equals 0. And let's take a look. We have 120 equals 4 V Thevenin, which then we have our Thevenin voltage is 30 volts. 30 volts. So this whole circuit here, we can simplify this whole circuit to a single equation. And the equation, we have our Thevenin voltage, and then a resistance, which is R Thevenin. And we said that this is equal to 30 volts, and then this is equal to 4 ohms. So, and here we have our A and B. So these two are equivalent to each other. Okay, so this is called Thevenin's theorem. Thevenin's theorem. So that was a quick example. We will now cover more about Thevenin's theorem. And I've noticed I've been spelling this incorrectly. This is not an I, this should be an E. That was incorrect. So now it is spelled correctly. Let's do an example problem that includes dependent sources. Dependent sources. So I'm going to draw a current source. And connected to a resistor. Connected to another resistor. Resistor here. And we have A and B. And then we're going to put in a dependent voltage source. Dependent voltage source. Dependent voltage source. And with that, this is going to be 2 ohms here. This one is 6 ohms. I forgot another resistor here. This one, there is a resistor here that is 2 ohms. And a resistor here that is 4 ohms. And this dependent current or voltage source is 2Vx, the dependent, and this is 5A. So this here is our Vx. So that is Vx here. So we have a dependent voltage source. So in our first step of doing Thevenin's theorem is to turn off all independent sources. And we will still do that. This is our only independent source. So turning that off are Our source is now off. It's an open circuit. There is no current flowing this way. There's no current flowing. But we still have this. And we need to know the voltage here to be able to solve for this voltage source. So how do we do this? Well, because of linearity, we can actually put a voltage source right here. And we're going to say that voltage source is 1 volt. 1 volt. And now let's solve this problem. So we're going to have we're going to call this I1. And this is going to be I2. And then this is going to be I3. I3. And let's take a look. Right, so I3 there. Okay. Now, continuing on, let's solve this. Let's start with I1 here. And doing our mesh analysis, we have, I'm going to start here. We have 2Vx, and that is negative to positive, so that's a negative 2Vx. And then we have plus 2 I1 minus I2, and that is equal to 0. And we will see here that if we simplify this, we have Vx is equal to I1 minus I2. I1 minus I2. And so continuing on, that is our first loop equation. And what we will do here is we'll do the second loop. Right? The second loop, we'll start here and go around. So we have 4 times I2 plus 2 times I2 minus I1 up here. And then we have plus 6 I2 minus I3 equals 0. So that is our second equation, number 2. And let's do our third loop, number 3, this over here, and we'll start here and go around. So we have 6 I3 minus I2. It's here. And then we have plus 2 I3. And then we go positive to negative here, positive to negative. So that is a positive 1 volt, and that is equal to 0. Okay? So now we need to solve some of these equations. So how do we do that? We also know from here that Vx is equal to negative I2 times this 4 here. That is Ohm's law here. And because it's positive to negative here, that is a negative I2 times 4. And we can put that into this equation up here. So we have negative I2 times 4 equals I1 minus I2. And continuing on, that's negative. So we have I1 is equal to, that's negative 4 plus 1, that's negative 3 I2. Okay, and we can use this result and put it into this equation here, into that equation. So let's first expand this out, this equation. So we have 4 plus 2, which is 6 plus another 6. That's 12 I2 minus 2I1 minus 6I3 equals 0. And we can sub this in for I1 here. We'll put this value right in there. So that becomes positive 6. So we have 18 I2 minus 6I3 equals 0. And then we can solve for I2. So I2 is equal to 6 divided by 18 I3, which is then equal to 3 over 9, 1/3 I3 divided by 3. Think. Okay. So with that, we can put, we can work on equation number 3 now. And let's just write that out. We have 6I3 minus, or nope, 8I3 minus 6I2 plus 1 equals 0. And we have this result here. This result here that we can use. And we'll put that in here. So we have 8I3 minus 2I3 plus 1 equals 0. And that comes out to be I3 equals 1/6 amp. 1/6 amp. And so if we go back up here, I3 here, is that negative? Is that a negative? Yeah, that should be negative. Negative 1/6 amp, negative. So if we go back up here, that means that the current coming out of this voltage source, I, is 1/6 amp. 1/6 amp. And we can use our linearity property then to solve for the resistance. Remember that the voltage is equal time I times R. And what we're looking for is the Thevenin here. So we have a voltage, which is 1 volt. That's what we put in. That's what we put in here, 1 volt. And we know the current, which is 1/6 amp. And we can find the Thevenin resistance then that way, which results in the Thevenin resistance here of being 6 ohms. So that is how we solve for the Thevenin resistance. So that is the first part of this problem. Now that we have the Thevenin resistance here, now we need to move to find the Thevenin voltage. So going back, let's get a new, and we then turn on the independent sources. So drawing this circuit again, we have our current source, which is 5 amps. And we have our resistors. Draw this. And lastly, our dependent voltage source here, which is 2Vx. And one more resistor here. So we are looking for, we have 4 ohms, 2 ohms, 6 ohms, 2 ohms. And we are looking for the voltage now, the voltage between here and here, and that will be the Thevenin voltage. So we have the Thevenin resistance. The Thevenin resistance is equal to 6 ohms. We just found that. And now we need the Thevenin voltage. So let's go through and solve this for the Thevenin voltage. Here, we will make our loops here. We'll call this I1, I2. I guess we should probably stay consistent. Let's back up. Let's call this I1, and then I2, and lastly I3. And we know that this, we'll call this I naught. I naught is equal to 5 amps right here. Okay? And we also know that our I3 is equal to 0 because it's open voltage. There's no current going through here. So I3 is 0. So let's do our loops here for I1. We have our negative 2Vx plus 2 I1 minus I2 equals 0. And remember, we found that out to be Vx is equal to I1 minus I2. Okay. And doing our loop analysis for, so that's our first equation. Our second loop here, we have, let's start here. Going up, we have a 4 times I2 minus 5 because this is 5 plus 2 times I2 minus I1 plus 6 times I2 minus I3, remember, but I3 is 0, and that is equal to 0. So that is our second equation here. So let's go ahead and solve, let's expand this equation, which turns out to 4 plus 2 plus 6. So that's 12I2 minus 20, 4 times 5, minus 2 times I1 equals 0. Okay. All right. And I forgot to write it in here, but this is Vx here. And we know that Vx is equal to negative I2 times that 4 ohm resistance. Okay, I2 times that, well, it's not I2 anymore. I guess that's incorrect, I'm sorry. Vx is equal to 4 times 5 minus I2. 4 times this current minus this current. So Vx is that, and we'll put that in here, which is equal to I1 minus I2. And so that is 20 minus 4I2 equals I1 minus I2. So that means, let's see, I1 is equal to 20 minus 3I2. All right, this is getting a little complex. And putting this into this equation now, so we have 12I2 minus 20. And if we put that in, that's negative 40 plus 6I2 equals 0. And we should be able to solve this pretty quickly. So that is 18I2 equals 60. Is that right? Okay, so that is I2 equals 60 over 18 amps. Now, what is our Thevenin voltage then? If we go back up, our Thevenin voltage here is going to be equal to I2 times 6. So that is this voltage here. Our Thevenin voltage is equal to that. So I2 times 6. So that is 60 divided by 18 times 6. And I need a calculator for this. That is, comes out to 60 divided by 18 times 6. That is 20 volts. So that is our Thevenin voltage here. And we've already found our Thevenin resistance here, which is 6 ohms. So our circuit would look something like this. We have a voltage source of 20 volts and then a resistor, and that resistor has a resistance of 6 ohms. So this is our Thevenin resistance, and this is our Thevenin voltage. And that was a long problem, but that is how you solve a Thevenin theorem problem that has dependent sources. Norton's theorem is very similar to Thevenin's theorem. We will now move from Thevenin to Norton. And they're very similar. So if we were to take a look at those, let's see. This is named after Edward Norton, and he was an American engineer and scientist, and he worked at Bell Labs, and this theorem is not as old as Thevenin's theorem. It's newer because Edward Norton lived from 1898 and died in 1983. So let's go ahead and take a look at Norton's theorem. Okay, so for Norton's theorem here, we are doing a similar idea where we take a very complex circuit. We take a complex circuit with voltage source, maybe a current source, and resistors. And we have two open terminals, A and B. And what we're looking to do is to transform those terminals, transform this circuit into an equivalent circuit that exists, that has a current source and a resistor And this current source is I Norton, and this is the resistance Norton here, the Norton resistance here. So we're looking at making these two equal, and that is the idea behind Norton's theorem. So what are the steps? The steps. So the steps, if no dependent sources, if no dependent sources, it looks very similar to our Thevenin steps. So first, turn off independent sources. So first, turn off independent sources. 2, find the equivalent resistance with the sources off, and that is equal to R Norton, which is actually also equal to the Thevenin resistance, And then the third step is turn on the sources. So once we find the resistance, we turn all the sources on. So we turn on the sources, and then we find the current, the short circuit current through A and B. So what we end up doing is taking a system and we short between A and B, and we try to find the I short circuit current, short circuit. So this stands for short circuit, and what that turns out to be is the short circuit current is equal to the Norton current source here. So these are the steps if there are no dependent sources. So let's take a look at an example now with no dependent sources and using Norton's theorem. Let's take a look at an example problem. And I'm going to draw a circuit that has both a current source and a voltage source in it. And another resistor here. And we're looking for the Norton equivalent between A and B here. And let's label these resistors. We have 8 ohms, 8 ohms. And then we have 5 ohms. And we have 8 ohms down here. And 4 ohms over here. And that is 12 volts. And this current source is 2 amps. So now let's take a look at the steps to do an equivalent Norton circuit. So the first thing we need to do is turn off independent sources. So turn off independent sources. So this current source becomes an open circuit. Here, that becomes open. This becomes a short circuit. A short circuit. Okay. So now we are looking for the equivalent resistance here, which is equal to the Norton resistance. Okay. So let's take a look we have, let's see, what's going on here? Do we have things in parallel in series here? Well, we can take a look, and since there is no current flowing this way, these two are in series. These are in series here, and so that would be 12 ohms. So let's redraw that circuit. These are in series, but these are also in series as well. So all of these are in series, here, here, and here. So I made a mistake there. Let's erase that. Okay, so that's 8 plus 4 plus 8. So that's 60, that's 20. So we have a circuit like this, A and B, and this is 5 ohms, and then we just said this was 20 ohms. So these are in parallel with each other. So the equivalent resistance there is 5 times 20 divided by 5 plus 20. So that looks like it's 100 divided by 25, which comes out to be 4 ohms. So that is the Norton resistance here. So we found that piece to the puzzle, and now we need to look at the short circuit current. So let's redraw the circuit. We turn the sources back on. And so we're just going to redraw the circuit here. And we have a voltage source there. And resistor, and a resistor. And we have A and B. A and B. This is 8 ohms. This is 5 ohms. This resistor is 8 ohms. This resistor is 4 ohms. And this voltage source is 12 volts. And this current source is 2 amps. So what we do now is we take a short circuit and we short circuit these two terminals. And we're looking for ISC here. That's what we're trying to find because that is equal to the Norton current. So let's keep going. Grab a different color here. All right. So how do we want to solve this? We can use, would it be useful to use KCL, KVL? We can choose what we want to use here. And maybe we want to do our mesh analysis where we have I1, I2, and let's do I3. So let's do this analysis. We'll start with this loop here. And what we find in that loop, I1 is equal to 2 amps. Okay, that's what we know about this loop. So let's do KVL around this loop now, our second loop, starting here. So we go negative to positive, that's negative 12 volts, plus our 4 times I2 minus I1, which we just said was 2, and plus 8 times I2, plus our 5 times I2 minus I3 plus 8, last one, times I2. Okay, and that is equal to 0. So that is loop 2. And around loop 3, let's do loop 3 now. We have loop 3, we have 5 times I3 minus I2 is equal to 0. Equal to 0. Okay. So continuing on, we have our 3 equations, 1, 2, and 3. Let's work on 2. Let's simplify 2. And we have negative 12, and then 4 plus 8 plus another 8. That is 20 I2. And then we have negative 8. Oh, I forgot this one here. That's not right. Not 20. We have 4 plus 8, which is 12, plus 5, which is 17, plus 8 is 25. 25 I2. And then with negative 8. Negative 8. And let's see. And then negative 5. Negative 5 I3 equals 0. Okay. So how do we simplify this? Well, taking equation 3 here, I think what we see here is I3 equals I2. Right? That's what we get from this equation here. I3 equals I2. So let's plug in I3 here. So we'll plug in I3. And what we have is negative 12. Well, negative 12 minus 8. So negative 20 plus 20 I3 equals 0. So that looks like I3 equals 1 amp. 1 amp. And so if we look here, I3 is equal to the current source here, I Norton. Oops, sorry. I3 is equal to I Norton, which is equal to 1 amp. So if we were to draw this, we would have 1 amp, and then we would put our resistance over here, and this would be A and B, and we found our resistance was 4 ohms. So this is our solution here to find this is our Norton equivalent. Norton equivalent here. So these two are the same. These two circuits are the same here. So that is an example of doing a Norton equivalent with no dependent sources, only independent sources. So for a Norton problem, Norton with dependent sources. With dependent sources. Step 1 is very similar. Turn off independent sources. Okay. Step 2, we apply either a 1 volt or 1 amp between A and B. Okay, so if we have A and B here, we either put a voltage source here, which is 1 volt, or it's your choice, it is your choice, or you can put a current source here of 1 amp between A and B. So this one or this one. And then you find the Norton resistance, because that is equal to the voltage across A and B divided by the current that you find so you can use this and find the current, or you use this and find the voltage. And then from there, you can find the resistance, the Norton resistance, using this equation here. And then the last step is turn on all sources. Turn on all sources. And then you find I short circuit. So you short circuit this and you look for I short circuit, and this is between A and B, and then that is equal to the current source, the Norton equivalent current source right here. So this is the steps if you have a dependent source. That means like a current source that is 3ix or something like that. A current source like that. So if you have a dependent source, you need to apply a voltage and use linearity to figure out the equivalent resistance, or the Norton equivalent resistance here. Let's take a look at the Thevenin versus the Norton. So Thevenin, we have the voltage source and we have the resistance. And in Norton, we have a current source and a resistance. This is A and B. Here and here. A and B. Okay. So there is a relationship between these two. A relationship between these two. R Thevenin equals R Norton. These are equal to each other. Okay? Likewise, there's another relationship between these two. The voltage Thevenin is equal to the current Norton times the resistance Thevenin, which is also, that is equal to the resistance Norton. So there is a relationship here between the two. So if you find the Thevenin, you can calculate the Norton, and if you find the Norton, you can calculate the Thevenin. Okay, so they're interchangeable and they're related in this manner here. This is how they're related to each other. So that may be helpful depending on which one you want to use. And really, you're just doing a source transformation. It is a source transformation. You are changing one source to another source. These two are a source transformation. Okay, so let's take a look at an example of a battery. So just a small battery. I'm going to draw an image of a battery here. Right. And in the United States, we call these maybe a AA battery. All right, we have our positive and our negative down here. And these are usually 1.5 volts. Each one battery is 1.5 volts. And so if we connect things up to this battery, for example, if I just run a wire from positive to negative here, what is the current? Right, well, we would maybe say that the current is infinite, right? It's very, very big, right? If we just connect two wires here. But our battery is not that powerful, okay? So in the real world, we don't actually get that out of there. So we can model a battery, and I'm going to model this battery. So what the battery usually looks like is a voltage source, and it has some internal resistance. So here is our battery, and this is 1.5 volts, and the resistance is roughly, let's say, 0.15 ohms, right? 0.15 ohms. So my question, so you can think of this as like a Thevenin resistance, right? Some Thevenin resistance for this battery. Okay, so we have this battery, and this battery then is equal to this circuit. Now, let's say I want the max power of the battery, So I want the max power. How much I want as big as possible from this battery here. And I'm going to put a resistor in here. So let's take, for example, if I put a resistance here, and this resistance is very, very, very small. Let's even go smaller. Okay. Now, the power, remember, is I times V. The voltage across here is going to be very small. This is going to be small. but this is going to be big. Okay? So the voltage is going to be small, but the current's going to be very big. It's going to go really fast through here. Okay, well, if I do another example of, and this time we still have our 1.5 volts, and this is still 0.15 ohms. Let's say I make this really big. So this resistance is equal to, I don't know, 10000 ohms. So if I do that and look at the power, it is equal to I times V. And this time, the voltage across here is going to be big, but this current is small. Okay? So this here gets a big current, but a small voltage. And this gets a small current and a big voltage. So if I want P to be as big as possible, what resistance do I pick? So what should the resistance be? If we know this is 0.15 ohms and this is 1.5 volts, if we want P to be big, actually what we choose for a resistance here, this resistance should be equal, to the Thevenin resistance for maximum power. So for maximum power, that's what we want. Okay? So if we want maximum power, we set max power, we set R equal to R Thevenin here. I would also like to add that the maximum power that you can get out of this system here, P max, is equal to the Thevenin voltage squared divided by 4 times R Thevenin. So in this case, our maximum power is equal to 1.5 squared divided by 4 times 0.15 ohms. And that would be the maximum power that we could get out of this battery right here.